Welcome to today's Explainer. We are diving into a genuinely fascinating convergence of music, law, abstract math, and computer science. We're going to unpack a comprehensive 12-part series on U.S. patent number 1266142, which you might know commercially as Cree DB. And, this really isn't just a technical blueprint. It's an entirely new vision for self-explanatory databases that could quite literally change how we build software from the ground up.
Right off the bat, think about this rather unexpected question. How on earth does an inventor with a background in music publishing and entertainment law end up patenting a totally new database architecture to solve a fundamental computer science flaw? I know, it sounds like the setup to an elaborate joke, but it actually resulted in a massive technological breakthrough that challenges everything we thought we knew about storing and executing data.
So here's our roadmap for today. We'll quickly cover 1. The von Neumann bottleneck, 2. Music law and databases, 3. The math of non-halting trees, 4. Surviving the Alice framework, 5. Beating the prior art, and finally, 6. The self-explanatory future. Let's get right into it.
Section 1. The von Neumann bottleneck, the challenge of decoupled architectures.
Okay, so traditionally, database engines and application runtimes are totally separated. You've got your storage sitting in one place and your computational execution sitting way over in another. This separation creates what computer scientists call the distributed von Neumann bottleneck. Imagine keeping all your construction tools in a shed down the street from the actual house you're trying to build. Every single time you want to do something, you suffer from latency and what's called serialization overhead. That is basically the incredibly tedious process of packing, traveling, and unpacking your data just to transfer it back and forth over a network. It is horribly inefficient.
When we look at the standard architectures we rely on today, like decoupled NoSQL or serverless function-as-a-service ecosystems, they're constantly fighting this high network latency and serialization overhead. I mean, you're always translating and moving JSON over TCP sockets back and forth. But the paradigm of the Hierarchical Script Database, or HSD, is completely different. It manages to have zero serialization overhead. Why? Because the computational script and the data share the exact same local memory context within a single node. The database and the application are completely merged into one living entity.
Section 2. Music, law, and databases, merging nouns and verbs.
To really grasp this leap in logic, there's a fantastic analogy from the inventor himself, Kyle McLean Smith. He compares traditional passive databases to isolated nouns and application servers to isolated verbs. His invention takes these traditionally separate elements and, well, finally puts them next to each other in a sentence. Suddenly you've got a database that doesn't just passively hold your data, it actively performs actions based on what it's holding.
And here's the wild part. This totally unique perspective, it didn't come from a traditional computer science background. Smith was actually a music business major at Belmont University, who then went on to get a law degree specializing in musical rights management. He's pointed out that without this interdisciplinary experience of mapping incredibly complex musical rights and royalty splits, he simply wouldn't have had the linguistic frameworks to even conceptualize this database program hybrid. It literally took an outsider's view of complex legal hierarchies to rethink basic computer science.
Section 3. Math of non-halting trees, Pythagorean triples, and scale symmetry.
Now, obviously, when you merge a database and an application, a dangerous new problem pops up. If these new active nodes keep programmatically spawning child nodes to handle new data, well, how do you stop the whole system from crashing due to a Stack Overflow error? A Stack Overflow is basically when a computer gets trapped in an infinite loop of creating new tasks and just completely runs out of memory. To prevent this fatal crash, Cree DB relies on geometric scale symmetry derived directly from Pythagorean triples. Yep, that's the exact same a squared plus b squared equals c squared equation from high school geometry.
By defining a very specific scaling ratio, where x equals c minus b all over a, the system maps out structural growth using 3 spatial partitioning terms. You have movement toward a vanishing point for nesting your data, your current physical position, and movement away from the vanishing point for expansion. By modeling recursive growth with this exact scale symmetry, the database achieves a non-halting tiling system. Think of it like an endless digital mosaic that automatically resizes itself mathematically, so it literally never runs out of room. The data tree dynamically scales without hitting recursion limits or memory overflows, no matter how deep the events go.
Section 4. Surviving the Alice framework, navigating 35 USC Section 101.
If you know anything about patenting software in the US right now, you know it is notoriously difficult. Under the strict Alice and Mayo legal framework used by the USPTO, patent examiners apply a two-pronged test. First, they ask, is the patent claim directed to a judicial exception? Things like a pure mathematical concept, a law of nature, or just an abstract idea. If it is, they move to step 2. Does the claim integrate that abstract idea into a practical application that provides a meaningful technological solution? Basically, you can't just patent math. You have to patent a specific technological improvement that uses that math.
Looking neutrally at Federal Circuit precedents gives us a pretty clear dividing line. Simply calculating data mathematically, like the Stanford haplotype phase case, or the Simio precedent, which just used generic computer functions to process object-oriented models, is generally deemed an ineligible abstract idea. You can't patent that. But on the flip side, consider the Addis precedent. In that case, a specific physical hardware-based data structure that functionally improved the technological encoding process of RFID tags was found fully patent eligible. Why? Because it conferred a concrete technological improvement.
So, how does Cree DB fare? Well, it navigates this legal minefield perfectly by landing firmly on the eligible side of the spectrum. It doesn't just claim abstract Pythagorean math, it integrates that geometry into a highly specific, practical application, an improved executable data structure. Its nodes run localized scripts to handle incoming events, and they automatically self-reproduce by spawning child nodes. It fundamentally and physically improves how a computer allocates memory, executes code, and scales data. It passes the Section 101 test with flying colors.
Section 5. Beating the prior art, distinction from Wallerstein and Swenson.
But getting a patent isn't just about eligibility. You have to prove your invention is genuinely novel compared to existing technologies, which is known as prior art. Evaluated against its closest peers, Smith's system stands completely apart. Take the Wallerstein patent, for example, which relies on a centralized network controller routing events against static, rigid rules, or the Swenson patent, which uses clunky, manual, human-driven workflow trees. Smith's hierarchical script database is vastly superior because it has a unified interpreter. It features programmatic, automated, self-reproducing nodes. The database essentially builds, updates, and mutates itself organically based on incoming events. It doesn't need a human or a centralized controller telling it what to do. It's honestly almost biological in its design.
Section 6. The self-explanatory future. Real-world embodiments.
This patent actually outlines several amazing real-world embodiments that show how this translates from theory to practice. There's a communication appliance where the database nodes natively listen for and react to SMS texts or phone calls. There's an educational quiz driven entirely by dynamic node states. But perhaps the most fitting embodiment, and this ties right back to the inventor's origins, is the music and rights database. The exact millisecond a streaming event occurs, the parent node receives the data, immediately executes its own script, and automatically spawns child nodes down the tree to calculate and record complex, fractional royalty distributions for artists, instantly, with zero network lag.
What's really exciting is that this architecture is already moving way beyond theory and into the open-source community. Take the Cheerbot project, for instance. It utilizes Cree DB on low-cost Raspberry Pi devices, acting as an incredibly lightweight, script-driven DevOps engine. Developers can automate local network routing and device behaviors through a unified console, completely bypassing the need for heavy, complicated cloud configurations. And this same architectural philosophy is extending straight into Web 3 with proposals like ERC 7827, bringing these precise, self-executing, self-explanatory principles directly to decentralized blockchain environments.
It is just an incredible shift away from standard database logic. So I want to leave you with this final provocative thought to wrap up today's explainer. As developers and everyday users alike continue to seek viable alternatives to heavy, expensive, centralized cloud architectures, how will these dynamic, localized, self-evolving database nodes reshape the way we interact with technology and ultimately build the decentralized web? The intersection of law, math, and code might just be the blueprint for the next era of the internet. Thanks for joining us to explore this remarkable journey.